Have you ever seen an insect just walk on water and thought, how in the world is that possible? It seems to defy physics, right? Well, it's not magic. It's an invisible, stretchy skin on the surface of the water. And today, we're going to pull back the curtain and see exactly how it works.
I mean, just take a look at this. It's a water strider, just hanging out on a pond like it's solid ground. It's not floating in the water, it's literally standing on top of it. But how? This thing is definitely heavier than water, so it should just sink. So that's the big question, right? How can something that's heavier than water just float? It feels like it breaks one of the basic rules we all learn. But the secret isn't magic. It's a powerful, invisible property of water that we actually see in action every single day. To really get this, we need to think about water in a totally new way. Imagine for a second that it has a thin, invisible skin right on its surface. And you know what's cool? Scientists use almost the exact same analogy. A more formal way to put it is that the liquid behaves as if its surface were covered with a stretched elastic membrane. Basically, think of it like a trampoline, just waiting for something to land on it. Now, the official name for this stretchy skin is surface tension. At its core, it's just the tendency of a liquid surface to want to shrink and pull itself together into the smallest possible area it can occupy. So, what in the world creates this invisible skin? Well, the answer isn't really on the surface. It's much deeper, down in the water's structure. We've got to zoom way, way in to the molecular level, where it's almost like all the little water molecules are holding hands. This whole incredible effect really just boils down to one simple idea. Water molecules love to stick together. You can think of them as billions and billions of tiny little magnets, all pulling on each other. And of course, in science, this attraction between molecules of the same kind has a name. It's called cohesion. It's basically the stickiness that water molecules have for their own kind. And this diagram shows you exactly why that stickiness is so important. See the molecules deep inside the water? They're getting pulled equally in every single direction by all their neighbors. So all those forces kind of cancel each other out. But the molecules right at the surface are a different story. They have no water molecules above them, so they only get pulled inwards and sideways by their neighbors below. And that strong, constant inward pull is what creates that tight, tense skin on the surface. And water is an absolute champion at this. Its molecules form these extra strong connections with each other, giving it one of the highest surface tensions of almost any common liquid. That number you see, 72.8 millinewtons per meter, might not sound like a lot, but for a force we can't even see, it is surprisingly powerful. Okay, so we have our stretchy skin, and we know it's created by all those molecules holding hands and pulling inward. Now let's go back to our water strider and finally solve the mystery. So let's look at our water strider again. See how the surface of the water actually bends under its feet? It's creating these tiny little dimples, pressing down on that elastic membrane. But that membrane is strong enough to hold, and it refuses to break. This diagram shows the physics perfectly. The insect's weight, that's Fw, is pushing down, but that stretchy surface does not want to be stretched. The surface tension, shown as Fs, creates an upward force as it tries to flatten itself back out. As long as the insect's weight isn't enough to actually break that tension, the water just pushes back and holds it right up. So, the crucial point is this. The water strider is basically standing on a molecular trampoline. It's an expert at distributing its weight just right so that the upward push from that surface tension can support it. And just like that, mystery solved. But this incredible force isn't just for insects. It's also the master artist behind some of the most common and honestly beautiful shapes we see water make every single day. So remember, that inward pull is always trying to make the water's surface as small as it can be. And for any amount of liquid, the one shape that has the absolute minimum surface area for its volume is a perfect sphere. That's the most efficient shape there is. And once you know to look for this, you'll see it everywhere. Just look at the water droplet on the leaf, pulling itself into a tight, perfect little bead. Or on the right, as water drips from a faucet, you can watch surface tension literally pinch it off and mold it into a sphere in mid-air. It's physics acting like a sculptor right in front of us. It even explains why puddles have that sort of domed shape. You think gravity would want to flatten the water out completely, but surface tension is fighting back, pulling all those water molecules together and holding the puddle in a defined shape.
Oh, this is one of my favorite visuals for this idea. A soap film on a wire frame will naturally form the shape with the absolute minimum surface area possible. This is the exact same principle that pulls a water droplet into a sphere. It's just a beautiful demonstration of physics, finding the most efficient shape, all on its own.
So this skin is pretty strong, but what happens when you actually want to break it? Well, the tools for breaking this tension are probably sitting in your kitchen right now. Soaps and detergents are specifically designed to do this. They belong to a class of substances called surfactants, which is really just a short way of saying surface active agents. So how do they work? Surfactants basically force their way in between the water molecules right at the surface. They break up that cohesive hand-holding, and that dramatically weakens the surface tension. You can see the effect here. The water stops beating up and just spreads out flat. This is exactly why soap is so good at cleaning. It allows water to penetrate everywhere instead of just sitting on top. So surface tension is this hidden force that lets insects walk on water, that shapes every raindrop, and that dictates how puddles form. It's an invisible architect shaping the world of water all around us. The only question left is, now that you know what to look for, where are you going to see it next?